As I mentioned before, the fundamental equation for torque is a cross product equation. So torque, the vector torque, is equal to the lever arm vector crossed with the force vector. Now the cross product gives us a vector answer, and it also multiplies the components of R and F that are perpendicular to each other. If we are able to find those perpendicular components, we can approach finding torque the way we have so far. I want to show you how to do the cross product though. Let's say, for example, we had a wrench that was angled. Such that the lever arm vector that points from the rotation axis, so the center of the bolt is where the rotation axis would go through, out to the edge, that's where we're going to apply the force. I'm going to make these numbers up, so I can't say that they're actually right or that they represent an actual wrench. I don't know how long the handle of a wrench is off the top of my head. So this R vector is saying that it has an X component pointing to the right that's 10 centimeters long and a Y component, 12 centimeters long. Now the force we're going to apply, let's say we're going to pull, and this force we're going to apply, F, it has an X component. Let's say it's 20 newtons. And it has a negative Y component. So let's see, it's smaller. So let's make it 8 newtons. So again, I'm making these numbers up, but for the purpose of showing you how to do the cross product. Now, there's nothing wrong with trying to figure out the angle between these two vectors. As we've mentioned before, we can say that the torque is the magnitude of the lever arm, the magnitude of the force, times the angle between them. We can totally find the angle between them and solve for the torque that way. And that is perfectly valid. To do the cross product, though, we set up a matrix. So when we're saying that R cross F is, in the top of the matrix, we put the unit vectors. So I, J, and K. In the next row, we put the components of R. Now I'm going to solve this symbolically first, and then we'll come back and solve it with the R and F that I have made up. The last row of the matrix, we put in the X, Y, and Z components of the force, the second vector in the cross product. So cross products are not unique to our torque equation. The torque is simply one example of a cross product. So we're setting it up this way. When we actually solve the cross product, we're taking what's called the determinant of this matrix. You may have already learned how to find the determinant of the matrix, and that's fine. Do it the way you have learned. I'm going to show the way that I like to do it, because it's the way I've learned, and it is the way that gives me specifically the X, Y, and Z components of the answer right away. So to find the X component of my answer, I cross out the column in the row that have I hat in it. So I'm crossing out the top row and the left column, and that leaves me with these 4 uncovered numbers. I start with the top left of the numbers that are not uncovered, and I multiply it by the diagonal. So F sub Z, the Z component, is diagonal to that Y. And then I subtract the other 2 uncovered numbers, And this all together ends up giving me the x component of the torque. And to have the torque having an x component, if you remember in the previous video, if I put my thumb in the direction of x, my fingers show me which way around the x-axis any rotation would occur. And that's what it means to have an x component of torque. Now, in the case of what I've made up over here on the left, there will not be an x component of torque. This wrench is not going to rotate at all around the x-axis. I would need to have some sort of z component of force to make that happen. But again, I'm just showing you how to solve for the determinant of the matrix. To get the y component, I'm going to slide this over so I have more room. The y component is always negative. That has to do with matrix rules, so just go with it for now. I'm changing my highlighter because I have to cross out row and column again. So pretend I can't get the yellow gone from the first highlighter without erasing my home matrix. So I'm just using a different color of highlighter. So imagine those yellow numbers are now uncovered. Once I've crossed out the row and column that j hat is located in, I start with the first uncovered top left number, which would be x, and I multiply by its diagonal. So I have to jump over the y's because they're covered. So x times fz minus fx times z. So I always start with the top left uncovered number and multiply by its diagonal, and then I subtract the other two diagonal letters that are uncovered. So this whole thing would give us a y component of torque. Finally, the z component, let me choose a new color. Let's see, blue. I cross out the row, so the top row and the column, that far right column, and the uncovered numbers would be right here. So I start with the top left and I multiply by its diagonal, and then I subtract the other two numbers multiplied by their diagonals. This would end up giving me a z component of torque. Now, as far as we're concerned this semester, most of our torques will be around a z-axis, but conceptually, just having a torque around a specific axis means there's some rotation of the object around that axis. If you take statics, for example, you will do many problems that have three-dimensional forces, lever arms, and so you will get torques that have x and y and z components. They call it moment in statics. I'm not sure why we use different terms, but the process is the same. You can set up a determinant of the matrix and solve. So let's come back to these numbers that I've made up. So we have this wrench with the lever arm, we know the x and y components, the force, we know the x and y components. If we're asked to calculate the torque, torque is R cross F. So I would set up my matrix, and the first row is always the unit vectors. The second row is always whichever vector is first in the cross product. So in that case, that is R. I'm going to put these in terms of meters. So 10 centimeters would be 0.1 meter. The j hat, the y component, is 0.12 meters. And then there is no z component. And those zeros are important in terms of calculating the torque. The last row is always the second vector in the cross product. The x component is 20. The y component is -8. And we don't need to put the units in there, but we can. So this is what our matrix will look like. So just to practice, the cross product. To find the x component of this torque, I cross out the top row and the left column because that is where I hat is located. Starting with the top left number, 0.12, I would multiply by its diagonal, which is 0, minus the other two numbers multiplied, the other two diagonal numbers, which is also 0, so this whole thing ends up being 0. There's no rotation at all around the x-axis, is what this is telling us. Similarly, the y component, again, that y component is always negative. It just has to do with the location within the matrix. You don't need to worry about that, just remember that. I cross out the top row and the middle column because that's where J is located. Starting with the top left number, 0.1, so the top left uncovered number. 0.1 times 0 minus the other two diagonal numbers. But again, this one ends up being 0 as well. When there's no z component of the lever arm or the force, there does not end up being rotation around the x or y axis, which we probably could have anticipated that from the beginning. Now the z component, crossing out the top row, the last column, that leaves me with these four numbers uncovered. Starting with the top left, 0.1, I multiply by its diagonal. And then I subtract the other two numbers. Oops, 0.12. Now this, of course, is not going to give us a 0. The torque, if we plug in those numbers, I'm getting negative 3.2. The units are Newton times meters. Newtons for the force, meters for the lever arm. And then K hat. So the magnitude, which just the numerical value would be 3.2 Newton meters. The direction would be negative K hat. What that means in our traditional Cartesian coordinate system, K, the z direction, points out towards us. So having a negative z direction means pointing away from us. If you take the thumb of your right hand, excuse me, sorry, and point it away from you, having the torque point in the negative z direction, so your right hand, your thumb's away from you, your fingertips being arrows, your fingertips would represent rotation this way or clockwise around that axis. So that's what it means to have a torque in the negative z direction, is that it's this wrench will rotate clockwise because of this force. So clockwise around that negative z axis. Now, as far as torque problems are concerned, whether you use the cross product or what we've been doing so far in previous videos, whichever one's easier to use. If you can find the angle, then for sure, just run with this. That's fine. The main situation I would solve the cross product for is if the information is given to me in terms of components. So if my lever arm, my force are already in terms of components, it can be easier, I guess, to set up the matrix and just solve for the determinant of the matrix. Solve the cross product that way, rather than taking the time to figure out the angle between R and F. So, but both work just fine.